Hi there, in this video we're going to go over convolution. Now let's imagine we have two functions of time, say f of t, and we've got a function h of t. Now we can convolve these two functions together, and that's the symbol we use for convolution, a little star. And when we've convolved them, we will generate a third function, g of t. Okay, so that there is our convolution. Now it doesn't tell us very much. We need to go and have a look and see what this operator is doing. Now we'll draw it out using an example, and from the example we'll be able to show you the function, the derivation of the function, or a graphical derivation of the function. So let's imagine we've got a function f of t, and let's say f of t is a square wave. Okay, so it's length 2, height 1, that's t, this is f of t, right? And let's say our h of t, h of t is a triangular wave. Okay, so let's say h of t looks like that. Okay, so that's h of t, and that's say 1, and say the height there is 2. Okay, now what we're going to do in order to convolve these is we've got to pick one of them. It doesn't matter which one it is, so let's say we pick h of t, and we're going to take h of t and we're going to flip it over this axis. Okay, so we're going to take it and flip it over the axis, and we're also going to introduce a dummy variable called tau. Okay, so tau still get units of time, but it's just a dummy variable. So to flip that on that axis, h of t would become h of minus t. Okay, so that would be h of minus t, and we'll change the variable to tau. So we're going to end up with a function there, h of minus tau. Okay, now this still just stays the same. Okay, so we've still got 2 and 1 and t, and we'll change the variable in that as well, actually to tau. Okay, so that's got the dummy variable tau. Now the idea here is to take the function there and slide it along this axis. Okay, so in order to slide it along the axis, we have to add on increments of time t. Okay, so for example that could be t1, t2 and t3. So if we slide it along, say to t1, then we would have that function there but slid along the axis. Okay, or that function, it would be that point there if it was t2 slid along the axis, and we can just continue sliding that function along that axis there. Okay, now in order to facilitate that sliding of the function along the axis, we're adding on the values of t. Okay, so we could rewrite that there then as h of minus tau plus t. Okay, and that would facilitate this sliding of this function along the axis. Now of course what we do is we rewrite that as h of t minus tau. Okay, so what we want to do is we want to take this h of t minus tau and multiply it by a function f of tau, and when we do that there, we're going to get, now I'll draw out one of them. Okay, so to give an idea, so if we'd slip this along this axis, okay, so say that's at point, that's 2 and that's height 1. Okay, so we slip that along the axis, now let's say it went along to that point there. Okay, so when we multiply this here, which is our h of t minus tau, and this is our f of tau, when we multiply both these together, what we get is this little part of the function here. Okay, so we get that little height there. Okay, so we get that there as we shift that along. Now, if I was to shift it further along here, at some point this entire triangle would be encapsulated within this rectangle. Okay, so we would have, for example, that there. Okay, now this little part of the area here and this little part here, this would represent the value h of t minus tau f of tau. Now, in order to finish off the convolution and get our value of g of t, what we do is we integrate this function, okay, with respect to our value d tau, which really means taking this area here, okay, and the area there becomes the height of the function g of t. Okay, so we'll end up with a third function here, g of t, once we've shifted it along that axis, which will look something like that. Okay, so there's our t, and that's our g of t, and that there will be our convolved function. Okay, and the height of the convolved function here at these points equals the area that we have whenever we multiply our h of t minus tau by our f of tau. Okay, so the convolution is going to then, if I rewrite it, is g of t equals the integral from minus infinity to infinity of h of t minus tau f of tau by d tau. Okay, now you might be looking at that and saying, well, why bother? You know, why bother with all this? Well, it'll become more apparent in later videos how useful this is. Now, but a simple idea here is that if this signal here is the input to a system, okay, and the system can be defined, say, in these terms here, then if we think about the very first signal that was to go into the system, well, the first signal to get into the system isn't this one, because that's the time lapse by 1 second. The first signal to get into the system is the one at t0. So if we want to shift this function in effect, or use this as an input to this system here, we would have to flip it on this axis in order to ensure that we get the first part of the signal come in first, and then the next part, then the next part, next part. So that's why we're shifting it round like this. We're flipping it in that axis, and then we're sliding it across. Okay, and of course that represents there's the input into a system. But I don't want to get into all that at the moment. That's for future videos. Okay, but it gives an idea of the convolution operator. Now I'll try and draw it out in 3D so that you can see the dummy variable. So if we had our, and again in a few minutes I'll show it in MATLAB, so you'll be able to see it in MATLAB. Okay, so if we had our function, let's call that our function, that's our function, if that's tau, that's h of tau, and I'll draw these little lines in here just helps to show it a bit. So that's h of tau, and let's say our other function here is our function there, and that is our f of tau. Okay, f of tau. Okay, so whenever we introduce this dummy variable, we'll end up with a t variable and a tau variable. Now we can actually draw those in a little kind of three-dimensional way. So what we're going to have is this is going to be flipped round about. So we're going to get, coming in, we're going to have this one here, the f of tau, and we're also going to have the, if I can draw that on the same axis. Right, we're going to have this here, okay, coming through as well. Okay, and that's going to be that's a f of tau, and that's going to be h of t minus tau. Okay, so if we call this here our t variable there, okay, and this is our dummy variable, which is our tau, so that's our tau axis there, running up that way, and that's our t axis there, running down that way. Okay, so if we were to wait for a certain length of time, and this function here was to come in and sit over the top here somewhere, then what in effect we would have done is, if we call that t0, we would have gone to a point, say here, t1. Okay, so say that's t1, t2, t3, t4, t5, and you could look at this as having modulated this function here, having modulated that function. Okay, so you end up with the very first bit that comes in as a small area here. Okay, and as we move further along, okay, we're going to get a bigger area coming in here, and as we move further along here, at some point the whole triangle here is encompassed within here. Okay, so in this axis here, we'd be beginning along here somewhere, and the triangle there would be somewhere here like that. Okay, and as we move further down, at some point the triangle would be actually coming out of this signal here. So further along here, we would have some part of the triangle there, come down to that point there. Okay, so we would have these different areas would be occurring along this t-axis, and what we would do is we would integrate this. When we multiply these two together, h of t minus tau by f of tau, we're getting these individual segments. Okay, and of course we're getting them all the way along because it's continuous, but I've just picked out discrete points. And then when we integrate with respect to our tau axis, then what we're doing is we're finding these areas. Okay, so these areas there, that area, those individual areas, and when we find those areas, we're going on to another function, which again is in the t domain. That's the t domain there, and we're plotting those values, okay, along this axis. So that's a particular area which will have a particular height, and then another area there with another height, another area with another height, and another area, the example going on like that. Okay, so we would end up with a curve that would plot like this, and it would come down like that. Okay, so it allows you to see the idea of the dummy variable. Okay, so it just allows you to split this time axis into two axes. Okay, so that's all we really want to say there about that. As I say, we'll go back and we can have a look, but maybe one other thing there before I go on and show you in MATLAB is that we can do the convolution in the frequency domain as well. So all we're going to do is just replace our time with a frequency. So you'd say, let's say g of omega equals the integral from minus infinity to infinity of, say, f of v h of w minus v by dv. Okay, so that's the same thing, and it's the exact same, looks exactly the same within the frequency domain as well. Now let's have a look and we'll see if we can bring it up in MATLAB. I'm pretty sure I've got it set it up there yet. Okay, so there it's in MATLAB, and what I've got here is our function f of t. Okay, just there, and our function there. It's actually a swap version of it. I think the function we used was in this direction, but it doesn't matter. We're taking this function here, h of t, and we're going to flip that function h of t over this axis, so when it comes in, it'll actually come in like that. Okay, but you'll see that just in a second. So if I can find MATLAB and bring it up and enter. So there you go. You can see the function coming along here. It's been flipped in that axis. Oh, can you see it now? Yeah, flipped in that axis, and it's continuing along here. Okay, and this is the convolve function in the bottom. Okay, and you see it's heading back out of this function here. So the area is dropping down and down and down and down and down and down and down till they cross over 0 again, and we can get into the very end. Okay, so that there is our convolution. Okay, so we've taken the square wave and the triangular wave. The triangular wave's been flipped in this on the axis and then shifted along the time axis, and the area, overlap area, has been calculated, and the overlap areas are the height here. Okay, and this is the convolved function g of t. Okay, so that's all for now, and I'll get back to you in the next video. Okay, bye bye.